Morning, folks. So I sent out a Piazza note this morning about testing, and also included some more information in Lab 3. And the suggestion is that you're going to want to start by simulating one node with 4 zero-value boundary conditions, and remember that the maximum size of rho for stability is 0.5. It must be strictly less than 0.5. I suggest starting with 0.25. And you may as well not start with a huge initial condition. In fact, you're going to want to set un to un minus 1 for the initial condition, because that implies u of time n equals u of time n minus 1 implies that the velocity equals 0. And if you set un equal to some value like 1/8, and you set un minus 1 initial to 0, you've just implied an upward velocity of 1/8 of a unit per time step, which is fast. So these initial conditions may well overflow, whereas these will not. Okay, so make sure you set the initial conditions so you don't get overflows. Then I would say, and that's what I want to have for this lab. Tomorrow night I want you to simulate 10 nodes. There's 10 nodes. So yeah, required MATLAB output, simulated 10 by 10 array. Once you get one node, you can build it by hand. I would say by the time you get to about 100 nodes, though, you probably want to use a generate statement. Keep the error rate down. Next would be, so Lab 2, I want to see that same 10 by 10 array, or an improved 10 by 10 array, using the audio codec on the FPGA. So that says by Lab 2, you have to have the complete busmaster state machine running for the audio codec. And then Lab 3 will be your gigantic parallel processor. So I want to stage it this way so that we don't see people spending 100 hours the last week on this project. Any questions on this? There's a bunch of comments that have come up. One was parameter choice. How do you choose what eta delta t over 2 should be? How do you choose rho 0? And then there's rho effective, which is rho 0 plus a function of u squared. How do you choose the gain for that? You're probably going to want to do that first in MATLAB, and then take it over to hardware. I would say that eta delta t over 2 should be something like 2 to the minus 9 or so. Might be a little smaller. And the reason for that is that you smack a drum, it's running at 100 hertz, it rings for how many seconds? 2 seconds? 3 seconds? If it's ringing for 1 second, that's 100 cycles. And therefore the damping must be significantly less than 0.01. The damping per cycle. So you want the damping per cycle to be rather low. Rho has to be strictly greater than 0 and less than 0.5. The nonlinear parameter, you're probably going to want to make the effective nonlinearity change rho by 10, 15%. So the rho effective might be greater than or equal to rho and less than 1.2 times rho 0, something like that. In any case, this value has to be less than 0.5. Any questions on that? How many people got one node working? Okay. Any gotchas that you found in that? Did it work as advertised? No. Because you start out with an 8 of 0.5 and it went like this. Yeah. Because the damping at 0.5 is something like a half the amplitude per cycle. Something like that. One group asked me how to set initial conditions, and there's a couple of ways. One is use an M10K block as a ROM, a read-only memory, that has a two-dimensional Gaussian programmed into it. So this is a Gaussian of revolution, right? It's axially symmetric around this axis. So it's something like e to the minus mu times x squared plus y squared, right? With the appropriate offset for the center, so it has to be x minus center squared plus y minus center squared. And generating that in Verilog is going to make you cry. So a possibility is to calculate at MATLAB, build a ROM table, import the ROM table. I did this for a sine wave, and you can use my template code for generating a sine wave to generate a table, if only I can remember where it is. I think I'll go looking for that. But an example on the Busmaster page is down in at the bottom, the top level module. Down at the bottom of the top level module is such a ROM table. And if you declare a module as clocked with an address and an output, and every value is a constant on this side of the case statement, then Quartus will infer a ROM from it. Because if every expression over here is a constant, then you're never writing to it. So on the pos edge of clock, you take an address, in this case an 8-bit address, and it returns a 16-bit fixed point. In this case it's in 2.16. 16-bit fixed point. Actually it's in, 1.15 format. And so it's 2's complement, 16-bit, which happens to be the format that the audio codec requires or can use. So this is then outputting sine wave samples whose angle is given by in units of 1/256th of 2 pi radians, whatever that is. 256 values per revolution. So you can easily build a ROM table. And again, I have code someplace, I'll have to go looking for it, that takes an arbitrary value plotted in MATLAB and generates this table in Verilog. So I'll link that up on Piazza. You could build a 256 entry. So that would be a 16 by 16 template, Gaussian template. And then dump that into the center of a much bigger drum. You don't have to drive the whole drum surface initially. You just have to have a big enough region that it doesn't alias. And a 16 by 16 is big enough that it won't alias. So you could have a 16 by 16 template of Gaussian that you move out into the center of your drum or any place else on the drum. That way you could strike off center. That's cool.
When you reset your system, should you zero your memory, or can you assume that there's random data in your for each drum position and that it will converge to a?
The question is, should you reset memory to 0 when you start a simulation? And the answer is yes, because if you start with a random excitation, or if you start with what's left of the last excitation, then you'll get some weird mode mixing. It'll still work, but you could have some high energy samples in there like white noise, which would alias and cause some crashing sound at the beginning.
Will that always converge to a resting state? I mean, could you just zero it out? Could you just run your...
Yes, you could. You could, yes. If you run your system continuously, so it never stops running, it'll converge to a 0 state because it dissipates energy. And then if you start from that state, you're fine. You cannot, at reset time, issue a clear memory command. There is no such thing for M10K blocks. There's no clear memory. To do that, you would have to run a state machine that goes through all of the addresses and zeros them. One way I've done that in the past, this is so crude, is you ask yourself, how long does it take you to push a button and release it? Well, if you're really fast, it might be 60 milliseconds. So all the time that the button is pushed, you increment addresses, set the bus write to 1, and write them. And you just keep doing that over and over again, clearing everything to 0 as long as the button is down. When you pull your finger up, it's all clear. So you have a one-state state machine that just writes every possible address as fast as it can in reset. That's how I used to clear VGA memory when I was writing to it directly before the QSYS days where everything is a little bit abstracted. What other questions about Lab 3? We still need to talk about the audio codec some more and the audio state machine. But anything else, given that tomorrow is a deadline, any questions with regard to the deadline? So, after writing the bus master, the generalized bus master for the audio codec, I decided to start playing with some digital signal processing. So the DSP page has a slightly better worked out bus master because it's one more iteration of the code. And the logical setup here, oh, maybe I can get it off of QSys. So the logical setup is you're going to write a bus master which looks at the audio subsystem, watches the audio subsystem, reads from the audio subsystem, and writes to the audio subsystem from the bus master. The external connection of the bus master is going to be out to your drum. And then the audio subsystem is going to talk across a serial link to an audio codec which has been abstracted away, or almost abstracted away. And the way you completely abstract it away is that you need to set up the AV config module correctly. So AV config, which you can see down here, is connected to some sort of control slave on the audio subsystem. And what it does is at boot time, when you load up a design, AV config sends I2C commands. Remember I2C from, sends I2C commands out of the FPGA to the audio codec to set up things like sample rate. Do you want the ADC connected to the audio input? Do you want the DAC connected to audio output? How do you want this Wolfson chip, which I'll show you a block diagram of in a minute, configured? And the way you do that is with a handy dialog box here, audio video config, and in particular, you want the audio in path. You don't care about the audio in path right now, but you do have to click this, that the audio out should be enabled for DAC output. That connects the abstract FIFO, the abstract interface on the AV subsystem, on the audio visual subsystem, connects the audio system output to the Wolfson DAC. So you have to check that. You probably want to uncheck these two. The data format is left justified. 32 bits? Yeah, maybe. You could leave it there. Although the codec itself won't. Yeah, the codec does do 32 bits, but your code won't. So you could drop that to 16 bits if you want, and leave the sampling rate at 48 kilohertz. So you're going to need to do that. Given that you do set up the audio that way, then you should certainly refer to the audio core manual for details. But the heart of it is that this is a bus slave. The audio subsystem is a bus slave that's going to get input from your bus master, and it's going to output two serial streams to the DAC from two FIFOs, a left channel and a right channel FIFO. And you're going to have to look at these control registers to say, is there space to write into the FIFO? If there is space, I need to generate a new sample. In other words, run the model one time step. And if there is space, run the model one time step. and then load left and right data. You have to load both FIFOs. Even if you're only calculating one value, you have to duplicate the data. By writing into these registers, you push onto the FIFO automatically, which then gets serialized to the DAC output. And there's a programmer's guide here which says this is what the control interface looks like in this bus slave. There's a control word which has a bunch of read and write enables in it, which luckily you don't have to manipulate. Then there's a FIFO space that says write left channel, right channel, read left channel, read right channel, each 8 bits. The two reads are synchronous and the 2 writes are synchronous. You have to write both of them. You have to read both of them. So I'm not quite sure why there are separate counts, except that with separate FIFOs, it allows you to do weird things like write one channel from the HPS and the other channel from a bus master. If you wanted to have output from the ARM superimposed in one channel with output from a microphone coming in the other channel, you could do that. I don't know why you do it, but you could do it. So the control interface is the usual kind of memory mapped interface that we're used to. So again, you're going to wire up the bus master to the audio subsystem. Audio subsystem is controlled by AV config. The audio subsystem conduit is going to go out to the audio codec. It's hardware which mercifully we don't have to talk about too much. The real most interesting part of this is then, what do you have to do to actually control the audio module? And you need, since we're going to be building a bus master here, we have to pull all the wires to generate a bus master. We have to give addresses to read-write addresses. We have to read-write bus. We have to read to write data, have to manipulate other controls. And so we start by setting up the appropriate addresses. I put the audio controller at 3040. And then there's offsets to the FIFO address, the left data address, the right data address. And the only way I could debug this, the only way I could figure out to debug this was to put the bus master control signals on the GPIO pin so I could look at them. In particular, I wanted to make sure that I was writing at 48 kilohertz exactly. And there's 2 parts to the state machine. There's going to be a part where you read the output FIFO. If there's space in the output FIFO, then you generate a new sample, put it into the output FIFO. And then there'll be a separate section where you read the input FIFO to see if there's data from the ADC, from the audio input. You read the input FIFO, and if there's a sample in the input FIFO, read it. Now, you're not going to need to do that because you're not taking any audio input in. So you're not going to do that. In this example, I'm gearing up to do audio filtering. So this first example is just a loop back that reads the ADC and writes it to the DAC. I wanted to make sure I could do that before I started putting filter modules in so that I knew that I had a control path that made sense. You're not going to be reading anything from the analog input. So the second half of this state machine you don't need. But in any state, in any case, there's going to be a reset state which zeroes all of the bus controls, a timer which I use just for debugging and for state machine control occasionally. And then in state 0, we're going to read the audio FIFO address because we have to find out if there's room to output a new sample. You're going to set it to bus read. Bus byte enable, we need all 4 bytes because the right channels are in the upper bytes of the word. And we jump to the next state. And in the next state, we're going to decide whether there's actually room in the FIFO or not. So here we actually read the FIFO. So if the bus ACK is high, we know that the FIFO space has been loaded into the bus read data, and we're shifting it 24 bits because the left channel right FIFO size is in the top byte. So bits 25 through 31. Now we have to check that there's actually room in the FIFO, because now we know how much space there is. And remember, this state machine is going to execute much, much faster than the FIFO becomes ready. This state machine is running at 50 megahertz. It's going to run 1,000 times before there's space in the FIFO again. Now, in your case, you're going to insert a giant state machine in here for doing the drum update. So the overall effect will be that you get about 1 sample every 48 kilohertz. I said here that if FIFO space is greater than 2, why did I say 2? I'm not sure why. Why not 0? And then we're going to take the left audio output and copy it to bus right data. Set the address to the left data, enable some bytes, enable all the bytes because I'm sending 32-bit data, do a bus write, but then there's an else if there isn't enough space, we just go back to state 0 and check again. If there was space in the left channel, then there must be space in the right channel because the two are synchronous. So we don't have to do a separate check. Write the left channel only if there was space. Now we write the right channel, and we don't have to do the FIFO check because the two are synchronous. And then if we were going to read, we would go into the next section of the state machine, which I don't think I'll go through right now. But every time you get here, you could set a state variable that says, I just sent a sample, calculate a new one. So I will scroll down here to the end of the read, because in this code I was getting ready to do audio filtering. So whenever I read a sample, whenever there was a valid sample that had just been read, I wanted to fire off the state machine and do one digital sample. I would do one digital DSP sample. So I made a data ready flag at the end of the read, which is here. So when I check that the bus ACK is true, after reading the second channel, I set an audio input ready flag wait a sample, and then clear it. So it goes high for one bus cycle. You would probably put such a one cycle state toggle after you do the write bus ACK. You finish writing the second channel. You set a flag high that says ready for a new calculation. The calculation starts. By the time there's space in the FIFO again, so many microseconds later, 20 microseconds later, you will have calculated a new drum value. So you're going to put a start flag here. If your state machine is synchronous and fast enough, you only have to bring it high for one cycle. You don't have to do any sort of acking on it. You don't have to do anything. You just throw it over. You just set it high for one cycle. The other state machine picks it up and starts running. So after you write both channels, the FIFO in both channels, you're going to bring a line high, start the new calculation. Is that clear?
Can we run this state machine at a faster clock rate? Or should it be synchronous with?
You can, as long as this state machine runs fast enough to not, so that you always keep some value in the FIFO, it's good enough. Now another possibility is, for control is, you check for FIFO full. If FIFO is full, you turn off your drum simulator. As soon as there's space in the FIFO, you run the simulation once. And so the output will be 128 samples behind your calculation, but since it's happening at 48 kilohertz, that's only 3 milliseconds, you'll never notice it. But you do have to synchronize them some way, either with a start command or a FIFO detect command, because you have to do precisely one drum update, all of the nodes, every time there's a slot in the FIFO.
Last time, or a couple lectures ago, you strongly recommended against gating the clock to achieve something like that.
Well, there's sort of the, the clock distribution network is a special network on the FPGA, which is distributed, as far as I can tell, by isochronous network. It's a Hilbert tree through every path through the clock network is the same length, so that all of the signals arrive at the logic element synchronously. As soon as you gate a clock, it takes it off of the clock network and puts it through a logic element. And now it's no longer a clock signal anymore. It's not running on the clock network. And there may be significant clock skew in a large design. Better not to do that. But you can interlock a state. You can lock a state to wait for a signal before it can drop out of reset or drop out of start. So the audio interface is rather straightforward. It, excuse me, and you shouldn't have to modify the state machine virtually at all, except to change how the interlock signal works, because you're not going to have any input unless you want to mix your drum with some other audio. Do a drum accompaniment to your voice or something. So oh, and just for giggles, this has nothing to do with this lab, but I built a decimator, a rate reduction unit, so you could take in data at 48 kilohertz, decimate it to 8 kilohertz, which is correct for voice, and then do audio filtering at the decimated sample rate. Anybody know the origin of the word decimate?
Roman punishments are Roman. It was like Roman soldiers, and they would have 10 men. They had to kill one of them.
Line them up, kill every 10th one.
Yeah.
And it's deci as a prefix. Yeah. Now, I don't see having to be that harsh. But decimation here means that you're chopping out samples, hopefully without losing more information than you have to. So let's go back and look at lab 3 again. Any questions about these readings? There's a lot of readings in here. There's the equations I put on the board were essentially out of the study notes on numerical simulation of the wave equation with the finite difference method. And the MATLAB program is based upon that paper. The spectrum analysis comes out of the 2D waveguide mesh paper. Nonlinear effects comes out of circular membranes paper. And then all of these seem to be related to possibilities for parallelization on FPGA. So the two parallelization schemes I came up with were by block and by column. Anybody come up with another one? I don't know if checkerboard works or not for wave equation. It does for some equations, but I don't know that it does. It's sort of a leapfrog where you update the odds and the evens and the odds and the evens. I don't think that works for wave equation. But again, this week, 10 by 10 array with the ability to listen to the output of the drum in MATLAB. So you have to be able to copy the output vector out of Model Sim into MATLAB and play it through the speakers. Next week, 1 week from tomorrow, same 10 by 10 array or an improvement on it, running on the audio codec on the FPGA. So this is physical output from the FPGA. By the way, we have a bucket of speakers. Remind me to show you where they are. I have a tote full of speakers. There should be no problem with speakers. At this point, I'm not too concerned. If you have the nonlinear row running or not. It can be constant row. By here, I think you should have a nonlinear row, which I think I gave as row effective is the min, the max of 0.49, and row 0, where row 0 is some value that you pick initially, plus uij quantity squared times some scale factor that you get to pick. Was that squared also? I think so. Doesn't matter. It's just a constant.
It's
It's what? No, I don't want anything bigger than a max. I don't want anything bigger than... No, you're right, it's min. I'm full of it for a change. Yeah, there you go. It's the min. This guarantees that you'll never get a value equal to 0.5, which you could get if you choose rho naught close to 0.5. Let's see, 0.45. And then u squared times this constant gets to be as big as 0.5. You don't want to do that. The effect will become that the system becomes unconditionally unstable and will go into produce full amplitude feedback and tear the eardrums of the TAs right out of their head. Yes?
What's the reasonable choice for that constant?
So all of the Uij are less than are within -1, less than or equal to 1, right? So I would say that you're going to want an S which is certainly less than 1, and probably something like, you might want to change rho by 20%. So this should scale to like 0.02 or so. So the delta due to this should be like 0.02. So S has got a, so S squared is going to be something like 0.04, 0.02.
And what's a good choice for rho naught?
Oh, I'd start with 0.25. That's the middle of the range, right? That's safe. It's a good idea to do this in simulation first. You can certainly do it in MATLAB. You could say for a nonlinearity, for a static nonlinearity like this, what does it sound like? Can you hear the nonlinearity? Boom! You should hear a pitch sweep. You hit it hard, you hit it loud, it should be a higher pitch and then drop off as the amplitude drops. The pitch should drop as the amplitude drops. And that's physical. Real drums do that. So you want to set this constant so that it's audible but not ridiculous. Real drums have a fairly small effect. It depends on the drum. But and some drums can be a frequency shift of maybe 10%. My signed multiply, by the way, is set up for 2.16 notation. You may, if you want to change this to 1.17, what do you need to do? Let's see, multiplier, code snippet, multiplier. So we're putting two 18-bit numbers in, signed 18-bit, and that's important. These have to be signed wires so that Quartus compiler can infer a signed multiplier from the signed inputs. So when you then use a star here, Quartus is going to infer a DSP unit doing a signed multiply with a 36-bit output. Of those 36 bits, the binary point is at bit 31, 32 boundary. The binary point is right there because we have two 16-bit fractions multiplied together gives a 32-bit fraction, right? And we're taking the last bit, the 35-bit, which is the sign bit. We're taking the high order bit, the ones bit, and then we're taking 16 more bits after that by taking bit 35, the sign bit, and then bit 32 through 16, which is 17 more bits, to make a total of 18 bits of output. So to switch to 117, that means now that the sign bit, or the sign bit is still bit 35, right? So this is 2.16, 1.17. And the boundary between the fraction and the units digit is now, what's that bit?
34.
This bit is 34. This one is 33, right? Yeah. 2 bits over from 31, right? Because we added a bit to the fraction times 2 is 2 bits over. So you're going to have to modify this to be bits 34 through so that'll convert you to 1.17. Truthfully, you could probably use 2.16 and it would be okay. 1.17 will give you a little bit better sound. The advantage of staying with 2.16, I see a lot of side conversation. Did I make a mistake?
No.
Because that's usually what that means. The advantage of staying with 2.16 is you have a little bit of overflow capability. So a value of 1.01 won't kill you. With 1.17, if any value goes over 1, you're done. It'll wrap. And a wrap, in this case, means a large amplitude change from positive to negative. That's output to the audio codec as a 2-volt edge at full bandwidth. You know what that sounds like? It sounds like a loud, loud pop. And if you do that, say, 50 times a second, it sounds like a GAU-9 cannon. It's a Gatling gun. It's a bad sound. Okay? So decide on the arithmetic system you're going to use and stick with it, knowing the trade-off between 2.16 and 1.17. Thank you.